All right, welcome to lesson 5.12. Here we're going to identify and describe the characteristics of the logarithmic function and understand these functions to be the inverse of exponential functions. Very, very powerful, very widely used in real life and in further math courses. So let's go ahead and get started. Okay, so in order for us to discover what logarithmic functions are, we're going to take a look at an analogous situation that does not have any exponential expressions and try and apply the same reasoning to a situation that I'm going to present in a second with an exponential. So I want you to work through this piece by piece. I'll uncover them as we go, work on them briefly on your own, then press play and we'll move on to the next one. So start off with this. What operation must be applied to both sides to solve this equation below? Apply that operation, but do not solve. So the operation, of course, is taking the square root of both sides. So that will look like this. This is the radical symbol, taking the square root of both sides. Okay, let's move on to the second portion. Okay, so now what I want you to do is replace the green radical symbols with a verbal description of what the square root operation does to the value it is applied to. So in other words, write in words, and I'm going to write it in green here to represent the radical symbol. What does it mean when I apply the radical symbol, and then leave it as applied to and let this number fill in the blank? Okay, so the radical symbol, whatever your description is, will equal and let this fill in that blank. All right, so I'm going to show you what I would write for this side, and you can then translate it over to the right side if you were struggling with it the first time. So the radical symbol means to me this. When I apply the radical symbol to something, I'm looking for the number that multiplied by itself is equal to blank, or whatever that number, this value is, which is 25. And so there I've written it here. So reading this again, the number that can be multiplied by itself to equal, and then whatever this value is. So when I apply the square root to a number, that is what I'm looking for. And so I can easily say the same thing on the other side. When I apply the square root, I'm looking for the number that can be multiplied by itself to equal x squared. Okay, let's move on to part C. All right, so why does it make sense to do this to both sides? And then once you've answered that question for yourself, show the solution. This will lead you into the solution. All right, why does this make sense? Well, it makes sense from a very fundamental standpoint. Think about the right side first. We're applying the square root, which means that we're looking for the number that can be multiplied by itself to equal x squared. We'll think about that for a second. What is the number that can be multiplied by itself to equal x squared? Very simply, it's x, because x times x is x squared. So when we apply this operation, what are we left with? We're left with x. So it makes sense to apply this operation because we're trying to solve for x. And so applying this operation allows us to, what you would say is, undo the squaring and be left with just x by itself. Working on the left side of the equation, we're asking ourselves, what is the number that can be multiplied by itself to equal 25? And in this case, we actually get two values, right? We could either have positive 5 or negative 5. So we'd write it as plus or minus 5. And there we have solved the equation. So the goal in solving an equation is to come up with an operation that will allow you to isolate the variable, and then applying it on the left side, or the other side, will allow you to find the numerical value to which it is equivalent. Okay, so now we're going to take this and we're going to try and use the thought process to work with an exponential equation. Okay, so here we go. Let's take a look at this exponential equation, 32 equals 2 to the x. What I want you to do is use this equation to fill in the blanks for this sentence. X is the number or power that blank must be raised to in order to equal blank. Do that now. Okay, well, let's think this through. X is going to be the power, and we can actually see that here, that 2 must be raised to in order to equal 32. So 2 must be raised to in order to equal 32. Okay, great. So with that little bit of verbal understanding, we can now think about how we might isolate x. So what I want you to do is, since we don't have this mathematical notation yet, you're going to write a verbal operation on both sides of the equation, just in the way that we did over here, that will result in x being isolated on one side. Now I want you to use the sentence in part A here and sort of the way that we constructed these operations over here on the left to help you create this operation. Take a couple of minutes, try some things out, and to help check if it works, go on to part C and ask yourself, why does this operation make sense? And if it allows you to solve the equation, then that's a good sign that you're on the right track. All right, if you were still struggling, I'm going to give you one more hint. Think about over here on the left side, when you ask yourself, what is the number that can be multiplied by itself to equal x squared? The answer was x, and that's what allowed you to isolate x. So over here, if you were to ask yourself, what is the number, blah, 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 that is equal to 2 to the x, your answer should be x. Hopefully that kickstarts you in the right direction. We'll take a look at the proper formation in a second. Okay, so here's what the operation should say. The operation should find the number slash power that 2 must be raised to in order to equal 2 to the x. Because think about what that is. Well, what's the number that 2 must be raised to if you want it to equal 2 to the x? Very simple, just x. And so we apply that same operation to the left side. And you ask yourself, the number slash power that 2 must be raised to in order to equal 32. And of course, whatever that number is whatever x is supposed to be. And so this allows us to solve the equation because we end up with x is equal to, and now we can ask ourselves this question, what is the number slash power that 2 must be raised to in order to equal 32? Well, think about this. 2 to the second power is 4, to the third power is 8, to the fourth power is 16, 2 to the fifth power is 32. So the answer is 5. And we can, of course, see that that works. 2 to the fifth power is, of course, 32. So this operation that we described verbally is, in fact, what's called a logarithm. And it is the inverse operation for exponentiation, or raising something to the x power. And it will allow us now to solve for variables that are in the exponent. In other words, to solve exponential equations. So let's take a look at them a little more in depth and learn the notation for them. All right, so I'm going to use the example that we just did to help make sure that we're understanding the notation here. So we had our exponential equation, and we're going to solve it by applying the logarithmic operation with a base of 2 to both sides. So what we're doing is we're taking what's called log base 2 of both sides. And what that means is exactly what we wrote. We're looking for the number or power. I like to use either one. It depends on your preference. The power that 2 must be raised to in order to equal whatever the argument is. So when I read this, I'm saying log base 2 of 2 to the x. And what that means is I'm looking for the number that 2 must be raised to in order to get 2 to the x. Over here on the left, I have the number that 2 must be raised to in order to equal 32, and that again is applying log base 2 to both sides. And I can read that as the log base 2 of 32, and what that means is I'm looking for the number that 2 must be raised to in order to equal 32. And of course that results in x being equal to, and I'll write this here, the log base 2 of 32. And we can actually compute this in our head, right? What must I raise 2 to the power of to get 32? Well, that's going to be 5, and so x is equal to 5. All right, so now let's take a look at this in the general case so that we can see how we'll apply this to any situation. Okay, so here let's look at the general form of an exponential equation. We have y equals b to the x. We're trying to solve for x here. So we're going to apply an operation to both sides that will allow us to isolate x. So on the right side, we're thinking about, okay, the number or power that what must be raised to in order to equal b to the x. Well, here our base is b, so we're thinking the number or power that b must be raised to in order to equal b to the x. So think about this. The power that b must be raised to in order to equal b to the x is just x. So that will allow us to isolate x on the right, and we apply that same operation on the left. We're looking for the power that b must be raised to in order to equal y. And now that we know how to represent this in a mathematically appropriate notation, we can do so. So over here we will have log base b of b to the x. And over here on the left we'll have log base b of y. And now on the right-hand side, think about what we have. Well, we're looking for the number or power that b must be raised to get b to the x. And therefore, we're ending up with x. And what is x going to be equal to? Well, it's equal to log base b of y, which is, of course, the number or power that b must be raised to get y, or to equal y. We can't say for sure what this is going to be, but this is how we represent mathematically what we're looking for, and that is, of course, the value of x. And so you can see here that you can go from an exponential equation like this and solve for x, and you now have a logarithmic equation. Now there are a couple very neat things that you might have picked up on already. The first is that whenever we have an exponential equation, we can solve for x by taking a logarithm of both sides. And we also then will notice that the logarithm is the inverse operation of exponentiation, or raising something to the x power. And what's great about that is it allows us to solve for x, in other words, to find the inverse equation of our exponential equation. And so not only have we just discovered a new mathematical operation, but this mathematical operation is in fact the inverse operation of exponentiation. And so we have now found the inverse function for an exponential function. So we'll look at all these details in more depth later on, but for now, let's go ahead and practice transforming an exponential equation into a logarithmic equation that we might be able to solve a little bit more easily. All right, so here are 4 equations for you to solve. Before you get started, I'm going to give you a couple of tips to help you out here. The first thing is that, remember, you have to follow the order of operations. And since exponentiation, or taking exponents, comes before multiplication, when you're solving an equation, you need to work in reverse. So you're going to have to take care of the multiplication before you take care of the exponent. And so you'll see what I mean. I'll go through the solution for number 1 here. And so I want you to try number 1 first, see what you get, and we'll take a look at the solution in a second here. Okay, so hopefully you got to the point where you solved for x and you had some logarithmic expression, and we'll talk about that in a second. But first, let's go over how you would solve this here. So first, I'm going to multiply by 1/2 on both sides to take care of the 2 here, and I'll have 15 times a half. Half of 15 is 7.5, 7.5. And over here, I am just left with 3 to the x. All right, now I need to isolate x, so I'm going to take the log base 3 of both sides. Why? Because log base 3 of 3 to the x, which will look like this, log base 3 of 3 to the x, is the power that 3 must be raised to get 3 to the x, which is, of course, just x. And then over here, I will have log base 3 of 7.5. All right, so this means, of course, that x is equal to log base 3 of 7.5. All right, now that is correct. Obviously, x is equal to the power that 3 must be raised to get 7.5. We knew that just by looking at the equation to begin with. But the question is, what is this number? Well, we can estimate it. Think about it. What must you raise 3 to get a number a little bit bigger than 7.5? Well, 3 squared is 9, so we have an exponent of 2 that gives you something a little bigger than 7.5. 3 to the first power is 3, so the power of 1 gives you a number less than 7.5. So we're expecting log base 3 of 7.5 to be between 1 and 2. Now, if you go to Wolfram Alpha, you can actually compute this value. So if you go to wolframalpha.com, you can enter log parentheses, the base comes first, so log base 3, and then the argument, so log base 3 of 7.5. Now I want to mention something here. You could put in 7.5, or 7.5 is 15 divided by 2, so you could also put in here 15 over 2, and then close the parentheses there. Hit enter, and you will get the value. So we see that log base 3 of 7.5 is approximately equal to 1.834. And therefore, we have a solution for x. X is approximately equal to 1.834. And you can test this out by using this x value back in your original equation. And since you approximated it, you might not get exactly 15 over here, but it should be very close. All right, you should go through now and solve the equations that remain, number 2, 3, and 4. One quick note here that will help you out. When you're putting e into Wolfram alpha, you can say log base e, and then whatever the argument is. So, for example, log base e of 10, and then press enter, and it will tell you what you must raise e to the power of to get 10. All right, make sure that you are checking your answers by plugging the x value back in, substituting the x value back into your original equation. You can use Wolfram alpha for that as well, and we'll take a look at the solutions tomorrow and then move on quickly to discovering more about logarithms.